So thanks everyone for coming. Today we have Alexander Schmidt. So go ahead.
So that's me to start. Okay, thank you for the invitation. And so let me give you the... Okay. And now I want to talk today about joint work with Katharina Hübner, and the title is Tame Cohomology of Schemes and of adic spaces. It works. Okay. So just as a starter, let's consider things over an algebraically closed field of positive characteristic. And we consider properties of the Étale fundamental group of varieties over K. And because we are in characteristic P, the behavior is not the best possible. So in general, the Étale fundamental group is not finitely generated as a profinite group. And the functor Étale fundamental group does not commute with products, which is ugly. And it is not homotopy invariant. Yeah, we know that already. The fundamental group of the affine line is huge by results of Renault. Of course, the first two items are okay if X is proper, but what one wants to consider, okay, what I wanted to mention is the result of Piotr, who proved that an affine variety in positive characteristic, this has no higher homotopy groups. So all affine varieties and characteristic P are K pi 1s, which one has to decide whether one thinks is great or is ugly. That means all the information is in a fundamental group, but we don't have any useful information in the higher Étale homotopy. So, and as a remedy for this, for many years ago, Grothendieck and Miller considered the Tame fundamental group. So let me fix the setting. Assume that X bar is proper and connected, and X is the complement of a normal crossing divisor D. So this means in particular that X bar is regular in the neighborhood of D. And then let's name the function field by Kx. And now we have finitely many components of this normal crossing divisors, and these correspond to discrete rank 1 valuations of the of the function field Kx. And then what do you see now? Do you that's bad. No, maybe that's better. Yeah, and then I try to. Okay, so the problem is that I could not see the full screen because of the video. Okay, so this is the setting, and this is well known, and the definition is that a finite Étale cover Y to X is tame along D, of course, if these finitely many valuations are tamely ramified in this extension of function fields. Yeah? And tamely ramified always means at most tamely ramified. So this is the definition, and tame covers defined in this fashion establish a Galois theory, Galois category, and one obtains a tame fundamental group, which I want to denote in this matter. And of course, for the fundamental group, we always need a base point, but I will omit this base point from the notation here. And of course, to be a tame cover is a further restriction to being an Étale cover, and this simply means that we have a natural surjection from the Étale fundamental group of X to the tame fundamental group. And this approach has a number of problems coming with it. First of all, if I give me a variety x, such x bar simply need not exist. Yeah, even if x is smooth, then it depends on resolution of singularities. And secondly, even if it exists, then it might depend on the chosen compactification, of course. And third is functoriality. So if I have a morphism x bar to x, I want to have a associated map on the Tame fundamental groups. But for this one, I had to choose these compactifications and the normal crossings divisor in a compatible way, and this causes problems. Okay, so what is the remedy? The remedy is to consider curves as test objects. So what do I mean by this? I mean, if you have a curve, so smooth or not, we always have a unique compactification. So this is a proper curve, or which is regular at the boundary and contains C as a open dense subscheme. So this always exists for curves, and that means that the question of the Tame fundamental group is canonical for curves. And now we use curves as test objects. That means we say that an Étale covers curve Tame if the base change to any curve gives a Tame cover of this curve in the other definition. So this is, of course, the minimal definition of tameness, which gives the accepted definition for curves and is stable under base change. So it seems to be a reasonable definition. And this gives a curve Tame fundamental group, which I denote in this way. And I again omit the base point. And of course, you can compare this with other different notions of tameness. And some years ago, I wrote a paper with Moritz Kerz about comparing all these approaches. And essentially, at least if the scheme is regular, all approaches are equivalent, or are equivalent if we believe in some weak form of resolution of singularities. And over a field, one can even do it without resolution of singularity by using results of Michael-Temkin. And the curve Tame fundamental group has some good property. For example, it's homotopy invariant. At least if X is normal, it's not so difficult to show that the curve Tame fundamental group does not change when passing from X to the affine line over X. And now we have a fundamental group, and starting from this, we can define the first Tame cohomology group. Because if I write here Étale, then it's known that the continuous homomorphisms from the fundamental group to a constant sheaf A is exactly in bijection to the first Étale cohomology group. And using this analogy, we can define the first Tame cohomology group of X with values in A. Of course, this is a, say, H1 for the poor, but we can do it. And then one can compare the Tame H1 with Suslin cohomology. So this is the following theorem by Thomas Geiser and myself. Unfortunately, we have to assume resolution of singularities. And then for any separated scheme of finite type, so there's no assumption on regularity or so, and any integer m, there is an isomorphism between this first Tame cohomology group and the Suslin homology, cohomology of X with values n z mod m. Yeah, of course, if m is prime to p, p was the characteristic of our field, then a covering of degree prime to the characteristic, a Galois covering, is automatically tame. That means also that H1 tame defined here is H1 étale if m is prime to the characteristic. And in this case, that m is prime to the characteristic, the isomorphism between the first Étale cohomology of X and the first Suslin cohomology of X was a theorem of Suslin and Wygotsky, or it was in the 90s, last century. Okay, and the case that m is a power of the characteristic, this was the new contribution of this theorem. So, and what we learned in this when writing this paper is that it's really ugly to have a theory H1 and not having H2 and higher and not a long exact sequence. So you have to make a lot of hand waving, having not all these long exact sequences. And moreover, if I assume that m is prime to the characteristic, so I can write étale here, then the theorem of Suslin-Wygotsky holds not only for H1, but for all dimensions and all degrees. And so it would be nice to have something like this also by replacing the Étale cohomology by the Tame cohomology. So our goal was define higher Tame cohomology groups, and of course they should come along as a sheaf cohomology of some site. And now we should not restrict to something over a field and even not algebraically closed field. So we work with schemes X over an arbitrary separated base scheme. And let's look how far we can go. Let's put some notation. So I didn't tell you what it is, but I will define, I will denote the Tame cohomology of, this is always a relative thing, so because it has something to do with compactifications of X over S, and F is a sheaf on the Tame side X over S. Of course, we should construct such a Tame side, but after having constructed the Tame side, I will use this notation for its cohomology. And we also want a natural homomorphism of sides between the Étale and the Tame side. And for sharper, better notation, I will give this morphism a name, so I will call it alpha. So what is our wish list for such a theory? First of all, it should be a geometric theory. So that means we want topological invariance. That means if I have a universal homeomorphism of S schemes, then the sides should be isomorphic, or if you want so the same, yeah? So this is well known for Étale, for the Étale side, and we also want it for the Tame side. And of course, prime to the characteristic, everything is fine. So we want a comparison theorem to Étale cohomology for invertible coefficients. That means we want the following property. If we have an abelian sheaf which is annihilated by some m, which is invertible on the base scheme S, then the Étale cohomology of an Étale sheaf should be the same like the Tame cohomology of the associated Tame sheaf. So the Étale cohomology was prime to characteristic coefficients is great, so we do not want to change this. And thirdly, for proper schemes, everything should be the same, like Étale cohomology, because then also Étale cohomology is good. So we want the following fact to be true. So if we have a Étale sheaf, and when X over S is proper, then Tame cohomology and Étale cohomology again should coincide. So the next hope is that this site has a natural notion of a fundamental group. And of course, we hope that at least under mild assumptions, this fundamental group should coincide with a curved Tame fundamental group, which had been considered before. Yeah, and then of course we want homotopy invariance. That means the projection from the affine line over X to X should induce an isomorphism on cohomology, at least for torsion sheaves. And then we want purity. So maybe I will say later a few words why this property is called purity. So we want, in the regular case, and an open dense subscheme, and we want this purity and positive characteristic. Then we want that the cohomology with values in the constant sheaf ZP is the same for X and U. So this is a property known by for H1 as defined before, and we want to have this purity statement for all dimensions n. So this is our wish list. And the key to the definition of the Tame site will of course be valuation theory, because tameness is a valuation theoretical concept. So, and now we do not want to consider valuations on a field, but valuation on a scheme. And so we have to define what we mean by that. So we have an S scheme X, and then we say an S valuation. There is a valuation on the residue field of some point. So we allow all valuations on all residue fields of points of the scheme X. These are the valuation, but now we have to say what is an S valuation. And so we want that there exists a morphism spec O V. So V is the valuation, which is a valuation on the field Kx. OV is the valuation ring associated with that. So we have here the natural morphism from spec Kx to spec OV. X is a point in X, so we have the natural map to X. We have the projection X to S, and we want this spec OV to dominate the point on S, which means that we get such a commutative diagram. So this is the notion of an S valuation. We made the assumption just for this talk to keep things easier that S is separated. So that means this phi here is unique if it exists by the separatedness of S. And to fix notation to the set of all S valuation, we denote it by val S of X. So this is a very general concept. Okay, sorry. And how do we denote elements of val S X? Of course, we have to first fix the point, and then the second component is a classical valuation defined on the residue field of X. So gamma is an ordered group, and of course 0 goes to infinity. So this is very general. So let us look for the classical example. So if S is the spectrum of a field, then S valuations are simply the valuations with trivial restriction to K. And if we are in an arithmetic situation, so as a spec Z, then there's no restriction. So every valuation is an S valuation. This is essentially the theorem of Ostrovsky. So now we define the algebraic side, the algebraic Tame side. So this will be the first approach, and the second approach will be the so-called adic Tame side. So what do we do? We define the Tame side in the following way. So the first naive approach, which only works for curves, is that you say take an Étale morphism and you say, when is it a Tame morphism? And for this, you ask for tameness along the boundary of a compactification. But this turns out to be too rigid. There are not enough morphisms, so one has to do something which is similar to the definition of the Nice-Nebich side. So the category we're working with is just the same as for the small Étale side. So we take all Étale morphisms from U to X. And the information sits in the covering. So a family of morphisms is a covering. If it is an Étale covering and an extra condition is satisfied, a tameness condition. So what do we want? For every point of U and every S valuation of U, there's one index, at least one index I, and the point Ui and the valuation Vi extending the valuation V. That means Ui Vi in val as Ui maps to UV. And we want that this extension of valuations is a tamely ramified extension in the sense of valuation theory. Yeah, and of course, if we have a Tame covering, this is by definition an Étale covering, and if we have a Nice-Nebich covering, then
excuse me. Can you recall what it means to be tamely ramified if your valuations have bigger height than 1?
So tamely ramified. So what is tamely ramified? You take the what is the easiest definition? So you make the base change to the strict tensorialization of the valuation rings, and then you ask that this is has degree prime to the residue characteristic. Yeah. Yeah. So does it? So I mean, in this case, this is classical valuation theory. Then, of course, after the base change to the strict tensorialization, when it's prime, when it has degree prime to the residue characteristic, then it's already immediately an abelian extension prime to. So it's Galois and abelian. So another definition of tameness would simply be you can dominate it by a tamely ramified Galois extension. And for a Galois extension, you define tamely ramified simply by asking the ramification group to be trivial in the classical definition of the ramification group, which is the subgroup of the inertia group with the same definitions you are used to. So, okay.
Thank you.
Yeah. So, and if I have a point over U so that the residue fields are the same, then of course this has no chance than other chance than being tamely ramified. or you can just say to vi equals to v if k of ui is k of u. That means any Nissenevich covering is immediately automatically a Tame covering. So that means in the language of sides that we have natural morphisms in these directions. Or that's to or to fix the direction. So I mean, it's not well defined in the literature whether the morphism goes in this direction or the other direction, but I like it very much to have it in this direction. Like so, as I said, there's no notion of a Tame morphism, but only of a Tame covering, which is a technical, not so pleasant thing. So then there are properties of this Tame side which are easy to show. So first of all, we have sufficiently many points of the side, and we have excision. That means we have, if you have this definition of a Tame side, you have also cohomology groups with support and a closed subscheme, and then we want a usual excision property to hold, and this is also not so difficult to show. Then the question after topological invariance, this is again okay, but you have to do a little work. So we have to understand what happens with the question of tameness when you make a completely inseparable field extension. You have to see that the ramification group stays the same, and then, but this is true, and that's why we get this topological invariance property as in the Étale case. And also the comparison with Étale cohomology for invertible coefficients is not so difficult. You have to consider the higher direct images of alpha lower star, and you can calculate them, or I can look at the stalks of this. I told you that we have sufficiently many points, and then show that the higher stalks vanish, or the cohomology of the stalks vanish when the stalks of the higher direct image sheaf vanish if the coefficients are prime to the characteristic. So this is okay, and now it becomes more difficult. So the first challenge is the following. So if X is a quasi-compact scheme, and we have an S-Tame covering, so S is always part of the notation. Sometimes I will just omit it, but because in the definition of Tame covering, all S valuations occur, that's why this depends on S. Then, of course, X is quasi-compact, we have a finite subcovering. And the bad thing is this finite subcovering is only an Étale covering a priori. So nothing says, nobody helps us by saying immediately that this finite subcovering is an Étale, so Tame covering. But we want to have sufficiently many quasi-compact objects in our topology, and of course we wish that quasi-compact schemes have this property. So the question is, do we find a finite Tame subcovering? By the way, this is also the same problem with Nissenevich topology. And the answer is yes, and the method of proof is that one has to give the set of S valuations on X a topology, and then the questions to show that the question of tameness is an open, or the property of tameness is an open property, and then you can use a compactness argument. All I wanted to say is that this is not completely obvious, and you have to do some work. But if you have this, then standard techniques like in the Étale case show that the usual theorems on the cohomology of co-limits of sheaves and of limit of schemes also for the Tame side. Yeah? This is then exactly copying the arguments of SGA form. So the second challenge is the comparison with Étale cohomology for proper X. So first, everything looks very promising. So if X over S is proper, then the valuation criterion of properness says that for every pair X V in val Sx, the valuation ring OV dominates the local ring of some other point. Yeah, let's look at this diagram. So we have this diagram. Phi exists because V is a S valuation, so this is part of the definition. And if X over S is proper, we can lift this to such a morphism. And that means that a ring with that if we have an Étale cover and we have this component where Y is covered, then in this component we find such a valuation which has the property even unramified and not only tame. So what I wanted to say is that every Étale covering of X is an S-tame covering immediately when X over S is proper. So looks that everything is okay, but the problem is that the tame side X over S does not only contain proper schemes over X over S, but also just take any open scheme of X. Usually it will not be proper over X. But the cohomology is of course an invariant of the side and not only of X. So the question to get this working is, can we calculate the cohomology of X by only using coverings of X? And if you think about this for a while, then you see that this is more or less equivalent to the question whether the Čech cohomology converges. That means whether Čech cohomology and Tame cohomology coincide. So what about the Étale situation? In the Étale case, Michael Artin has shown that Čech cohomology converges, and he has shown this from the Noetherian schemes, which have the additional property that any finite set of points has a common affine neighborhood. That, for example, if you are quasi-projective over a Noetherian ring, then this is okay. So now we want to use Artin's argument for the tame side. And so this gives the next problem, because the first part, so Artin's proof has two parts. The first part is a purely local part, which considers joins of Hensel rings, so which is also the title of this paper. And the second part, the global part, this uses Noetherian induction. And this is exactly the argument which does not work in the tame situation, because this set val Sx is not a Noetherian topological space. So what do we have to do? We have to go to this old paper of Artin and find another proof. So first that means we want to remove the Noetherian assumption in Artin's result. And then second, we hope that we can adapt the proof, the new proof for the Étale case also for the tame situation. And in fact, this works. What one has to do is to build a huge, in a sense, universal tower of Étale covering. So this is an idea that we learn from the Bud Scholze paper on the pro-Étale side. This technique also works for us here, and also we can adapt it to the Tame situation, and then show that under mild conditions, the Czech cohomology and the chief cohomology coincide also for the Tame side. And that means if we have now our Étale chief F here, and of course an Étale chief is a Tame chief physically because we just have less coverings, but to put it formal, I write alpha lower star F for the associated Tame chief, and then we see that the Tame cohomology coincides with Étale cohomology, and the Étale Czech coincides with the Étale cohomology, and then if X is proper, then the argument at the very beginning shows that the associated map between Tame Czech cohomology and Tame and Étale Czech cohomology is an isomorphism, and if we have an isomorphism here and here and here, we get an isomorphism here. So this was much work for this particular problem comparison with a Étale cohomology for proper schemes, but it worked. So comparison with fundamental groups. So the Étale fundamental group of a scheme is, as you know, defined as an automorphism group of a fiber functor, and the fiber functor is the fiber functor over a geometric point of the category of finite Étale morphisms to X. And exactly the same procedure yields the Tame fundamental group of an X scheme, S scheme X, but we have to replace the finite Étale coverings by the finite Tame coverings. What is a Tame covering? Now I have to say it. Cover. So the objects are finite Étale morphism with the additional property that for all choices we have tameness. That means for every y and big Y and every valuation, the extension here is at most tamely ramified. Okay, so we get a Tame fundamental group, and again by construction, this Tame fundamental group is a factor group of the Étale fundamental group, and equality holds if X over S is proper. And then the next theorem is if we are in a situation over a field and X is a variety, let's say of finite type, then the fundamental group of this Tame side in fact coincides with the curved Tame fundamental group. So the proof uses some very mild variant of, or the very first step in direction of resolution of singularities. This is the inseparable local uniformization of Michael Temkin. And in more general situation, if S is not over spec K, the theorem remains true if we assume some weak form of resolution of singularities over S. So, but there's a big technical disadvantage of the Tame side, namely we have this tameness conditions for all these valuations. These are many valuations, and the theory is not flexible in the sense that we cannot separate these valuations, as at least if they are valuations on the same field, for example. But this can be done using a second approach, the so-called adic Tame side. So how does this work? So the set of S valuation, I already told you that we can put a topology on it, but we can give it a structure of a discretely ringed adic space. So the space is denoted by spar X over S. So if X and S are affine, this is essentially spar of a Hübner pair, and then you have to patch these together to get a global spar XS, but this can be done. And then if we look for a morphism of adic spaces, the points on the adic spaces are valuation, and so there's a very natural notion of tameness. Yeah. So we assume that we ask this morphism to be Étale in the sense of Hübner, plus a tameness conditions on the ramification of the associated valuations. So, and now for any adic space, the Tame side consists of the following data. So the category, so this is what you expect now, so there's no subtlety in that. So the category is the category of Tame morphisms, and coverings are just surjective coverings, so surjective families. So, and this had been worked out by Katharina Hübner in a paper called the adic Tame side, and she verified standard properties of this adic Tame side. So this is a lot of work. So one has to adapt the methods of SGA4 from schemes to adic spaces, and almost in every single case you have to solve some extra problems which usually are rather difficult. And what is not a good thing? So the good thing is, now assume we are in positive characteristic. So this is a general phenomenon. If you want to compare, calculate cohomology with constant coefficients also, you usually associate the constant coefficient with some coherent information. Yeah, so comma sequence, Artin-Schreier sequence. And here in the p-adic situation, this is a big advantage of the adic approach. We have an Artin-Schreier sequence. Yeah, so this is GA plus. So if you know what an adic space is, then you know that adic spaces come with two structure sheaves with them, and so this is the smaller, the plus structure sheaf. And we have this Artin-Schreier sequence, and then one can try to calculate the cohomology of the additive group with plus, and this helps, without telling you any details, to prove the following theorem. If S is pure of characteristic P, and unfortunately some assumptions on resolution of singularities over S have to be done, and if X over S is of finite type, and U and S is a dense open subscheme, then we have exactly the two properties we wanted to have. We have homotopy invariance. So the Tame cohomology of the affine line over X coincides with the Tame cohomology of X. And we have purity. That means the Tame cohomology does not change when passing from X to U. So this is a lot of success, unfortunately still using resolution of singularities. And now we want to benefit from this by showing a comparison theorem between the algebraic Tame cohomology and the adic Tame cohomology. Yeah? So we take a sheaf F on the algebraic Tame side. There we have an associated Tame sheaf on this adic side, and we want that these cohomology groups are the same, because then we can get the homotopy invariance from the adic situation to the algebraic situation. And we had this problem already before, so this is not so difficult to show for the Čech cohomology case. So that the Čech cohomology of the adic space and of the scheme itself is the same. For its Tame version is maybe a lemma. Yeah, it's not so deep. And now the problem is, yeah, so now I call it a proposition. So of course, but this is not deep. Now we have shown that Čech cohomology of the algebraic Tame side coincides with the cohomology. So we have proven convergence on this side. So what we now need is convergence on this side. Yeah, so but it remains to compare the adic-Tame cohomology with the adic-Tame-Čech cohomology. And this is really difficult. So you have to reprove or to redesign the Artin proof on joints of Hensel rings to joints of Henselian Hübner pairs, and then you have to develop new techniques and use results from different sources. And even then, the naive result does not work. You have to use some comparison with the Riemann-Zariski spaces. So these are, or at least you have to use the set of Riemann-Zariski points, because the local statement you want to show is only true for Riemann-Zariski points. So let me just say Riemann-Zariski points are special points on an adic space. So not every point on an adic space is a Riemann-Zariski point, but we have a lot of them, and for these everything is okay. And then you can mimic this and indeed show the exact analog of Artin's theorem for the adic spaces. So if X is quasi-compact and a discretely ringed adic space, so this is all which we are interested at the moment, because we want to consider these adic spaces of the type spar XS, and these are discretely ringed adic spaces. And of course, we need some property again that any finite subset is contained in an affinoid open. And then for every F, the Čech cohomology and the sheaf cohomology coincide in the adic-Tame side. Yeah, and summing up, we now obtain the homotopy invariance and purity for our algebraic Tame cohomology by comparing it with the adic situation where we have proven already more. Okay, now next tasks are to come. So of course we should, and this is work in progress, we prove base change theorems for Tame cohomology. So that means proper base change and smooth base change. And we also want to prove the homotopy invariance in the mixed characteristic case, because unfortunately here in this theorem, the comparison between the adic Čech and adic sheaf cohomology only works in positive and pure characteristic P. So I'm not sure whether it will be true in the general situation, but we also want homotopy invariance and mixed characteristic for our algebraic Tame side. So let me come back to the introduction. So I said what we want to do is to have the comparison between Suslin cohomology and Tame cohomology also in higher dimension. And so let us consider the category of schemes of finite type over a field K. And then we want to consider correspondences on this category. So cork K is the same category, but with finite correspondences as morphisms. And then pre-sheaves on this correspondence category, these are, because the objects are the same, these are pre-sheaves with transfer on the category of schemes of finite type over K. So this is well known. And what we now can prove is if A is a finite abelian group, then the functor Tame cohomology on schemes of finite type over K, this is in fact a pre-sheaf with transfers on sheaf K. So this is in fact not too difficult, because you have seen in the beginning that our Tame side sits between the Nisnevich side and the and the Étale side, and this theorem is known for Nisnevich and it's known for Étale, and exactly the same proof also works for Tame. Sorry. What does one has to do? One one knows that the category of sheaves on the correspondence category, so the category of pre-sheaves with transfers, has sufficiently many injectives, and one has to show that such an injective sheaf is flabby when considered as a Tame sheaf on the category of schemes over K. Okay, so what we get is in fact a pre-sheaf with transfers. So this is, and this is true also for Étale cohomology, but the second part not. So now if we assume resolution of singularities, unfortunately we have, because we use Katharina Hübner's result on adic spaces. But if we assume resolution of singularities, then this pre-sheaf with transfers is a homotopy invariant pre-sheaf with transfers. So this is great. So this is what we hope for. And so the following, there's not really a corollary in the sense that it is obvious. So if X over K is a finite type and A is a finite abelian group, then in fact we can use some standard procedure, standard trick to associate a Tame cohomology of X with values in A and construct a map to the Suslin homology of A, and this in arbitrary dimension M. And of course we conjecture that these homomorphisms are isomorphisms. This is true if n equals 1 by the result of Thomas Geiser and myself, and it should be true if the torsion of A is p torsion free, because we have this isomorphism of Suslin and Vojevodsky, and the work which has to be done is to compare the maps, but this also shouldn't be too difficult. Yeah, so this is what I wanted to tell you, and I want to thank you for your, this does not work. Okay, so that's, I have to thank you for your attention.
Okay, thank you, Alexander. Let's give him a round of applause. Okay, we can get some questions from the audience.
I have one.
One in the chat from Oliver we'll take first. I'll read it out. Would it be an interesting task to look at Tame algebraic K-theory, or will it coincide with Étale algebraic K-theory?
Yes, I mean, the general philosophy is replace Étale by Tame everywhere and get beautiful theories. Yeah, but the first task is, of course, to prove all these basic properties which are known for the Étale case since many years. But of course, the idea is making Étale cohomology homotopy invariant by replacing it by the Tame cohomology. Yeah. And also, the site has, of course, homotopy groups. So now we get Tame homotopy groups, which are hopefully interesting and also hopefully not trivial in most cases. Yeah.
Okay, great. More questions?
So, if I may, I imagine there should be a notion of a constructible sheaf. in the Tame topology?
This is in fact tricky, so I'm still working on the correct definition.
Yeah,
So,
I understand that on the adic side, this might be very bad, but on your algebraic side.
no, even then, this is really subtle. So, I mean, you can write down a different. I mean, what one forgets is that to verify the basic properties of constructible sheaves in the Étale topology is also difficult. Yeah, and so I think this is work in progress, and it's one of the next things I will do to work out the notion of constructible sheaves. But we can, of course, assume that we will have some notion of constructible sheaf, which contains all locally constant sheaves with finite stalks and is stable under basic operations. Yes.
Right. Yeah, I was hoping like the push forward of FP along a finite type morphism should be constructible, right? Tame.
Yeah, this would be, of course, this is the theory one wants to show, that the higher direct images of constructible sheaves are constructible, which gives you finiteness theorems and so on and so on. Yeah, so I mean, the program is clear, so plug it into all the questions which have been answered for the Étale case under the assumption that the coefficients are prime to all the residue characteristics.
Can you remind us what the GA plus was in your entire sequence?
Yeah, GA plus, so an adic space is just 2. So it's the additive group of the plus variant of the structure sheaf. So you have so locally you have the Hübner pair, and Hübner pair is a pair of rings A and A plus, where A plus is a subring of A, which is integrally closed in A. So, and these, the A's, they patch to the global sheaf of functions, and the A pluses, they patch, so they glue, sorry, glue is the right word, they glue to a sheaf, which is the plus sheaf, and then you take the additive group of this plus sheaf. Yeah.
Thank you.
Okay, more questions. Anybody?
May I ask a question about the proof of A1 invariance? Does it deal only with valuations which appear because of product with A1?
Who's speaking?
Sorry.
Okay.
My name? Andrei.
Okay. So, and now again, your question.
Oh, yes, thank you. About the proof of A1 invariance, does this proof deal only with the valuations that are defined because of the product with A1? I mean, infinity of the affine line, and it defines valuation. Does this do we use in the proof only the condition for these valuations, or we need to use for all valuations? Maybe I can ask in another form. Let's consider base field case, and let's ask condition for rational curves in the definition of Tame covering, not for all curves, but only for rational curves. I mean, open subsets of affine line. In this case, for this version of Tame group, cohomology groups or fundamental group, would it be already A1 invariant if we ask only this?
But there are very few Tame covers. If you, I mean, you only want to check it at the boundary of rational curves. Is that what you said?
Yes.
But there might be no rational curves on your, take a higher genus curve, for example. Yeah, all morphisms.
Yes, I understand.
So if you consider only rationally connected varieties or something like that, maybe.
But when we take product with affine line, we get by definition a rational curve.
No, I don't understand. Probably I cannot answer your question.
Oh,
So,
okay. Sorry.
and for the details of the proof, maybe you should ask Katharina Hübner for the homotopy invariant. So I do not have
Okay.
present at the moment. So it's rather subtle. So you first prove purity, and then there's a standard trick to get homotopy invariance out of purity. So, but I do not remember more at the very moment. So I also had to look.
Oh, thank you. Thank you. In any case, thank you.
Okay, great. More questions, anybody?
Sure, well, a quick one. In your theorem comparing the fundamental groups, you were able to get away and not use resolution of singularities, but use Temkin's result.
Yeah.
Is there any hope that in the other points, like purity, when you use resolution of singularities, to use some kind of local uniformization instead?
Yes, there is hope, but no success at the moment. Yeah.
Mm-hmm.
So we hope that this can be removed from the proof, this assumption on. It's exactly one small point where it is needed, and we hope that Katharina will manage to remove the singularity resolution assumption from that. Yeah.
Okay. Thank you.
Okay, further questions? Excuse me. Okay, well, it doesn't seem to be the case, so let's all thank Alexander again, and yeah. Okay, so I think maybe Paul Arna can correct me if I'm wrong, but this will be the last seminar of the year, but we should be starting again in the spring. Is that correct?
Yes, that's correct.
Okay, so
See you all next year.
yes, see you all next year.